will build on the contents of the last video. After this video, you should be able to intuitively know what a molecule looks like just from looking at a diagram. Let's go back to the last video. In the last video, I taught you general rules about how oxygen, carbon, and hydrogen form bonds. Specifically, I told you how many bonds there are. Under normal circumstances, carbon forms 4 bonds, oxygen forms 2 bonds, and hydrogen 1 bond. Those 3 atoms are the most common atoms in all of chemistry. Let me also make one addition: nitrogen. Nitrogen is the 7th atom in the periodic table. It has 5 valence electrons, so it can form 5 bonds, right? No. That brings us to a new topic. I've said that electrons fit into shells, but how exactly? One of the best and easiest to see in your head, electrons could fit into layers of spheres. This packaging method is good. You can even imagine a utopia based around this. Electrons living in their layers, not bothered by negative charge repulsion. However, truth does not say so. What happened? Well, electrons are really fast. If you took a picture of a racing car at top speed, it would be blurry as the car would be moving too fast. However, electrons in a cable are moving at 80 to 90% the speed of light, so they're really impossible to capture. However, you can see the basic idea. Electrons zoom around, filling the space of each layer, and you can see that every layer is roughly spherical. Those layers are named atomic orbitals, or AO in chemistry shorthand. AOs have 4 types: S, P, D, and F. The outermost orbital is the S orbital on the first 2 columns. For instance, hydrogen has orbitals 1s1, lithium has orbitals 1s2, 2s1, magnesium has orbitals 1s2, 2s2, and so on and so forth. This way of writing orbitals are called electron configurations. There is a shortcut for writing AOs. You can write the name of the last noble gas in square brackets, then follow up. For example, the AOs of strontium can be written as krypton bracketed 5s2. P orbital comes next. Boron has orbitals helium 2s2, 2p1, carbon helium 2s2, 2p2, all the way up to neon, which has helium 2s2, 2p6. The d orbitals are then filled in the transition metal section, e.g. scandium, argon 3d1, 4s2, 4p6, titanium, argon 3d2, 4s2, 4p6, vanadium, argon 3d3, 4s2, 4p6, until zinc, argon 3d10, 4s2, 4p6. This time, D comes before S and P and starts from 3. Instead of the row, it starts in 4. The F orbital is not normally come across, so we won't talk about it here. Those orbitals are the key to bonding. When AOs merge, they can encourage electron exchange. This is called, you guessed it, a chemical bond. Now, S orbitals can hold 2 electrons. P orbitals have 3 directions: Px, Py, and Pz, and each direction holds 2 electrons. In all, 1 S and 1 P orbital can hold 8 electrons total. If nitrogen were to load 10 electrons from 5 covalent bonds into an 8 electron space, the space would overload and 2 bonds would not be able to form, since 2 electrons would get expelled from the group. Nitrogen, in fact, only forms 3 bonds. This way, it gets 5 electrons from itself and 3 electrons from bonding. It gets an octet and is satisfied. You just need to remember HONC, 1 bond for H, 2 bonds for O, 3 bonds for N, and 4 bonds for C. HONC, HONC. Remember Lewis diagrams? Those keep track of bonds and lone pairs, but they're actually not realistic nor simple. If you tried to use Lewis diagrams to denote a relatively simple molecule, you'd be here for quite a while. The first thing we can do to simplify the diagram is to avoid drawing carbon atoms unless necessary. Because carbon can form 4 bonds at once and be stable, they're common in molecules. This means that you no longer write the letter C, but keep the bonds carbon forms. Hydrogen is also largely unnecessary. Usually, you miss out both the letter and the bond. There are usually several hydrogen atoms attached to another atom, so you can always just deduct their positions. For example, a nitrogen atom with 2 bonds and no charge should have an atom attached to it. A notable exception is oxygen. When oxygen is bonded to hydrogen, you write OH instead of O. Sometimes NH or NH2 is also written. It depends on the molecule. We've made this drawing easy, but what about being realistic? To be realistic, you draw 2 bonds at a 120-degree angle. This can help to distinguish bonds, and real bonds come out somewhere in the region of 109 degrees. This makes your diagram much more distinguishable and recognizable. For example, try writing this molecule. Kind of annoying, right? Now see what this molecule looks like after simplifying it with our strategies. This is a lot better. Now try working backwards. How many hydrogen atoms are attached to this nitrogen atom? Yes, there's 2, because the nitrogen atom already has 1 bond. So now try drawing hexanol. Here's its Lewis diagram, and convert it using the ways I just told you. Well, yes, it is just a line. However, notice that you can still find the locations of all atoms. You can even know that there are 14 hydrogen atoms, none of which are on the diagram. We've talked about neutral molecules, but what about charges? Well, if the atom has a negative charge, it forms 1 less bond. And if it has a positive charge, it forms 1 extra bond. Be careful here. One thing could cause the other, so think carefully while dealing with charged atoms bonding.